welcome everyone to the OCaml workshop, bridge workshop by Sudha and Kaustubh. Thanks, Kaustubh and Sudha, for joining in. And we are glad that you came and could join us today. Yeah, over to you, Sudha and Kaustubh.
All right, so let me share my screen. So we have a live environment set up on Kaustubh's site for folks to use here. So let me ask all of you all to go to kaustubh.page/join. I'll give 1 minute for everyone to load the page. Ritul, by the way, one person has emailed me saying they have clicked on join, but the page is still loading and it doesn't seem to be loading.
I think things are working smoothly for the rest of the people. I can see 20 participants have already joined. So maybe he can try refreshing it and maybe rejoin.
Okay, okay. Sure, thanks.
Thank you.
All right, so this is OCaml top level set on the browser. So this runs with something called JS of OCaml. So JS of OCaml is this transpiler that converts your OCaml code to JavaScript and runs it directly on the browser. So we have set this up so that we don't have to go through the process of installation during the workshop. So this is the OCaml top level plus the Joy library, which we are going to use today, loaded in already. So this should be this should be enough to run everything that we are going to do today in the workshop, right? So let me give a sneak peek of what we have experimented with the Joy library. So this is a diagram that is generated by Joy code. We will see this towards the end of the workshop. There are more examples. So this is like a spiral staircase that was also generated with Joy. And this is something Kaustubh came up with yesterday, actually, tessellation, randomized tessellation example. There is also another one. So this is a flower sort of structure that was generated by only combination of rectangles. So let's jump in. So we have the live coding environment already. So if you look at the environment, you have the top level on the left, you have the Canva on the right. So the aim of Joy, so I can also show you Joy in case someone wants to check it out.
So this is the top level that we have. So this is basically an OCaml interpreter that is in the browser. And on the right, you can see there is some command of how to navigate the editor and some reference for how to use Joy. So the idea of Joy is that you start with very simple geometric shapes, and then you apply transformations on them, you combine them with other shapes, and then you come up with interesting patterns. And it's quite amazing how far you can go with building blocks like this. So you start with simple shapes, but then you have so many of them arranged in a particular way that you come up with patterns. So for example, so I want you all to try this, see if the interpreter works for you. Just create a circle and a rectangle. So like just start with copying. You can either copy the code or just say something like, let's see, equal circle with a radius of, let's say, 50. So this creates the circle shape. And in order to present it on the canvas, you have to use the show function with what is an OCaml list. and inside the list you pass all the shapes you want to render, and then it will show up on the canvas. So a few things here. How many of you have programming experience in some other language? Can you just react?
I can see 4 thumbs up, 3 raised hands, 5 thumbs ups. So I guess people are using it.
Yeah. So this is quite so this is how you would declare variables in another language. It could be like C equals something, right? So it's very similar. We give a name uh, to this function call. So we don't have parentheses. I mean, we have parentheses, but you can do without parentheses in OCaml. So like in Python, you would say circle parenthesis 50 parenthesis close, and it's different. So
Right. I am back. Thanks, Kaustubh. Sorry, I got to take an important call. Sorry for the disruption. Uh, so let's jump in. I think Kaustubh has also given an introduction of what we are going to see. So let's start with some basic shapes, right? So the Joy library lets us draw some basic shapes. Okay, let's call it circle. Why not? So I'm going to create a circle of radius 50. So my circle is created. It's called circle 1. So how do I display it in the Canva? I am going to do it with the show function. So so the nice thing about OCaml top level is it also tells you the types of functions, right? So if you see maybe I should zoom this in. So if you see the type of this function, it takes something called joy context. We can ignore it for now. It takes joy.shapes, which is basically a list of shapes. So this is an example of a list in OCaml. Let's say let my list L1 equal to 1, 2, 3, 4, 5. So this is my list. So show takes in a list of shapes and displays all of them in the Canva, right? So let's display this circle. This list is going to have just one element, but that doesn't matter. Oh, sorry, it's called circle 1. Right. So let's create a square. With the function square. Oh, sorry, it's called, there isn't a specialized square. It's a rectangle with side 100 and 100, which is basically a square. We can also see what the type of a rectangle is. Right? It takes a point which is an optional. Let's see what optionals are later, but let's focus on the important inputs. So it's going to take an integer, another integer, and it's going to return a shape. So these two integers are the length and the breadth of the rectangle, which we have given as 100, 100. So let's show the square now. So this is displayed on top of the circle that we have already displayed. Let's say I want a clear Canva. We just have to do a clear and we get a brand new Canva. All right. So these are the basic shapes. I'll give 30 seconds for folks to play around on their machine with the functions that we have just seen. By the way, feel free to stop us anytime on the chat. I don't know if it's possible to unmute yourself, but if it is, feel free to also unmute yourself and stop us if something is not clear, like through the session. All right.
Let's do a quick check to see if everyone is following us,
Hmm.
they're able to render and
Yes.
clear. Yeah.
Yes.
So,
So raise your hand if you have some trouble. Otherwise, we are going to assume that everything is in order. Okay, wonderful. Okay, so let's move on. So we have seen how to create basic shapes. So we can transform shapes. Like for instance, there is this transformation called translate. Right? Let's look at the type first. More often than not, one can reasonably infer what a function does through its type. That's I think that's a beauty of functional programming, and that applies for OCaml as well. So if you see the translate function, it takes uh, two integers and it returns a transformation. So the two integers are the x and the y distances of translation, assuming the starting is in the center coordinate 0, 0. Right. So let's see this example. I'm going to copy paste some things in the interest of time. Let me know if we are going too fast at any point. All right. So the first thing is, this is a circle of radius 50, which we have already seen before. Let's move this circle by 100, right? So this creates another circle. So let's display this one by one, right? So I think you know where C1 is going to be. This is the exact same circle we saw before. And if you look at C2, it has moved by 100 in the x-axis. So what happens if I move it by a minus 100? Okay, so now let's display C3. So this is essentially how translate works. We can also translate stuff on the y-axis, right? So if I translate only on the y-axis, this is what it's going to look like. And just for the sake of completion, let's okay, so this is essentially how translate works. Okay, let me clear this. And any questions so far? Okay, so in that case, you all are going to get an exercise. Can you see this image? Okay, so the exercise is with joy, create this pattern. And I think this can be done with just the circle function and the translate function. That is all we need. Okay, yeah, I'll give a few minutes, but in the meantime, feel free to ask any questions. I'm going to,
mm,
yeah.
and whoever is done, you can just react, raise your hand.
So Kaustubh, Sudha, there is a question for you in the chat, if you can answer, Julian. So how do we clear all images again?
Yeah, Kaustubh has answered in the chat. Yeah, just to reiterate, we can just do this clear function followed by 2 semicolons. So that will clear the Canva. So this, for people who have not seen this 2 semicolons, right? It's just something like terminate and run everything command on the OCaml top level. So this can be used in OCaml, but it's not mandatory to use this 2 semicolon to at the end of a function or at the end of whatever it is you want to execute. But this is like you're indicating the top level that run my code. There's also a single semicolon in OCaml. It's not a line terminating character, unlike in languages like C. So in OCaml, you can imagine colon as a line separator saying, okay, I have done this, do this next, sort of a thing. That is the difference between a single colon and double colon.
Julian
Why
has
do
a
we
good
need,
question.
yeah. Why do we need braces around negative numbers? I think it won't work without, as in it will, the order of execution will be different if we don't have the braces, and it won't take it as -100, it would take it as 0 -100, I believe, off the top of my memory, but we can test it. Yeah. So, yeah. This is taking the arguments as translate 0 -100. So 0 -100 is getting evaluated first, and that is being fed into the translate function. But the translate function expects 2 integers. It's getting only 1 integer. So that is why it's complaining here. So it's saying partial application. I hope, yeah, that answers the question. So has someone managed to get this shape yet?
We have one thumbs up.
Okay, wonderful. So do you want to share your solution on the chat box, maybe? Yeah, Lalit has shared their solution.
It'll be easier if you can just share your screen.
I guess. I think I should stop sharing the screen, maybe. I'll do that.
Yeah.
And maybe Lalit can share
I will
their screen.
unmute Lalit as well.
Okay, thank you.
Oh.
But I can brief, like I created a circle and whatever was the radius, so I moved it to all the 4 coordinates on all the 4 quadrants. So if the radius was 50, so I translated it to -50, -50, and similar way. So that's what I repeated for every circle.
Correct. Yeah, that's the perfectly valid solution. Thanks, Lalit.
Thank you.
All right. Okay, let's move on in the interest of time. So the next transformation is rotate. So we can rotate the shape by an angle. Let's see how that works. We are creating a rectangle. Let's display the rectangle. And we are going to rotate the rectangle by 45 degrees. Right? Before we do that, let's look at the type of rotate. So rotate basically takes an integer and returns a transformation. Right? So this integer is the angle of rotation. And in this case, we are going to rotate the rectangle by 45 degrees. So let's see. Yeah, and this is the same rectangle that is rotated by 45 degrees. All right. We can make really complex looking shapes with rotate, but before we try that, the next transformation is scale, where we scale the shape itself by some degree, right? Again, let's start with the same rectangle. All right. This is the rectangle. And we are going to get a rectangle that's scaled 2 times. So that essentially means the size of the new rectangle is 2 times the size of the original rectangle. All right. And I just realized we haven't introduced this operator. So this operator is essentially like feeding your input to a function. So scale is a function, right? So scale takes a float and it returns a transformation. So the transformation essentially takes a shape and returns a shape, right? So I can write this as scale 2.0 and rectangle. 100, 100. So this is also the same thing. But for better readability, what we do is we use this operator that lets us feed inputs into function. So there is another operator. This we won't need this today, but just for we have this other operator which lets us do this. It treat this the right hand side as the input for the function on the left. Right? Yeah, this is just for information. So let's see the scaled rectangle. Right, and now I'm going to scale it to half its original size. What does this look like? Right. So we have seen the 3 basic transformations: translate, rotate, and scale. So these are, these may look unassuming. These may look like really simple transformations. They are really simple transformations. But as we will see, right, we'll see how. Yeah, there's a question on the chat box. Why not do let S2 is equal to S1 scale 2.0? That is, yeah, that is perfectly valid. And that is also easier. Yeah, so as we'll see, we can do really complex stuff, complex looking images with these, right? So I'll let Kaustubh take over on the combining transformations part. I'll stop sharing the screen.
Okay. So, so we looked at a few of the transformations, and now we get to the really interesting parts where we can actually combine transformations on the same shape multiple times and get even more interesting patterns. So, for example, and I want you all to also follow along and also keep trying out things on the canvas. So if we start with a rectangle, like let's say 200, 200, and so what if we want to embed like what if we want to get this pattern? So by this by by trigonometry, we get that the sides need to be a little bit smaller. And for that reason, we have to scale by some factor after rotation. So we can do that quite elegantly with this. And there's one more hack on top of this that I'll get to. So we have this. We do show RR2. So one thing I did here is this is a list, and so this is how you separate elements inside a list in OCaml. In other languages, commas are popularly used. OCaml uses a single semicolon for separation. One more interesting thing that you can do. So in functional programming, the idea of composition is and using so-called higher order functions is like, you may have heard of these things quite often, right? Because it's a very powerful technique. So you take two functions and then you create a third function that actually is like an application of both of those in a sequence. And it's less intimidating when like I can actually show you what it does. So right now we rotated by 45 and then scaled by 1 by square root of 2. So okay, one thing that might catch your eye is we did not use the single slash for division. We used slash dot, and that is because of the float type in OCaml. So the OCaml has operators that act on just one type. So just slash is for integers, just slash dot is for float. So if I try to do 1.0 by 2, this will fail because it's expecting an integer, right? And the same thing goes for if I do this, because one's a float and one's an integer. What I need to do is this, and then two floats or two integers, then use the right operator. Right. So we chained these two transformations here, rotation by 45 and then scale by 1 by root 2. So we can compose these two into a single function called rotate and scale. And it's something like this. You compose, we give the first transformation, we give it the second transformation, and yeah. So now what I can do is, let me first clear the canvas. So I say let R equals, or rather R1 equals rectangle 250, 250. And let R2 equals R1, but then it gets rotated and scaled both, right? So what we end up with is the same pattern, but now we have like a single transformation that is a combination of more. And where this gets interesting is where we can use it as a higher order transformations, right? So if so now we get to another interesting operator, which is repeat, right? So repeat is repeat lets you repeat a certain transformation over and over, but every time you work with the result of the last application, right? And it's really cool because because you can apply a function in steps and capture each result So you can get like a progression of like the application, like if it's applied once, you can see it applied once, then twice, then thrice, then 4 times. And as an example, let's take a circle. We can start with we can start with, let's see, 1 equals circle 100, and let me, so this here is it's setting it's something called keyword arguments in OCaml, with like a wiggly and then the name of the argument, and this is how we represent a point in the coordinate space. This is how we represent a point. We don't need to do this. This is the same as saying a circle of radius 50, and then we translate it by minus 150. Right? So we translate by minus 150. And now we can try repeating a transformation on this. So we get a row of circles if we repeatedly move it by 20 units to the x in the x direction. So let's say let row equals C1, repeat 10 times the transformation, that is a translation of my translating by 20 points in the x direction, right? Then when we do show row, we get to see all of the circles. Right? One more cool thing, because I started with this rotate and scale. Now what happens if we apply it on a rectangle? So this is our initial rectangle. What if we say let rectangle is equals R? We pipe it into the repeat transformation where we apply 10 times the rotate and scale transformation. So when we do show rectangles, we get like a pattern where the next rectangle is like is rotated by 45 degrees and then 1 by root 2 times the side. So
I mean, start with this template. You can adjust the arguments, and that gives us interesting shapes. So I would encourage, let's probably take 5 minutes, maybe a few minutes, to just play around with this. And if you come up with some interesting shapes, you all feel free to show it to us.
and I've added a link to this document in the chat. So in case anyone wants to explore, get
Okay,
ideas.
wonderful.
Yeah. One more thing. So the editor allows you to share the code you have so far. So if you hit the share button, wait for a little bit, it will give you a link, which if you open, it will give you all of the previous code. Yeah. If you want to save your progress, whatever you've done, or like save the progress so far and then start fresh, you can create this link and save it somewhere and then continue. Again, it's
That
the share
is,
button.
yeah, that is very cool. It's easy to share or even save the progress that we have made. Okay, so we have seen how repeat works, and that is like a really, really interesting transformation that lets us create complex shapes, say in a line of code. And we have seen examples that do it. Okay, I'm just going to check if anyone has anything interesting to share before we move on. No pressure, but if you have something interesting that you want to show, do focus. So moving on. There are also colors built in Joy, right? So there are two ways you can use colors. So the first one is with stroke. What I'm doing here is I'm creating a circle of radius 50, and that has a blue stroke.
Oh,
Right.
Sudha, may I interrupt for a second?
Yeah, sure.
Girish shared a cool link.
Okay, I'm opening it. Oh, wonderful.
Yeah. And this is really cool because you see a circle in the middle, but there's no circle.
This is very cool.
I think if you try adding like
More rectangles.
that,
Yeah.
that would also be another pattern. This is cool. It's like a yeah, it looks like a rectangle. Then there's a circle in the middle.
That was very cool. Yeah, feel free to share more stuff that you guys have made. This so this circle has a blue stroke. There is also width fill that fills up the whole shape. Okay, so let's fill it with blue. Why not? Now this is going to give us a full blue circle. So a shape can have different stroke and fill. Like for instance, I'm filling this with blue and with stroke red. This is a perfectly valid transformation for the shape where it has a red stroke, but it is filled with blue, right? So let's see what that looks like. So this is the same circle with radius 50 that has red outline and that is filled with blue, right? Let's see how we can sort of juxtapose the repeat and other transformations we have seen earlier and play with colors, and let's see what happens. Okay. There is also this RGB function, right? It takes 3 inputs, red, green, blue inputs, and returns a color of that RGB. So the basic colors are encoded in Joy itself, but if you want more, more creative freedom to explore with more colors, we have this RGB function that, it can get us any color on the color spectrum. So I'm going to create pink, right? Let's see what pink looks like. What if I just do this? So this is the pink color we have made with RGB. And since we have not specified anything in the width stroke, it's by default black. But we can also make it a full pink circle if we want. So it's going to be with stroke that's also pink. So now we'll see a full pink circle. Right? Okay. So let's play around with this a bit. I'm going to copy paste stuff again in the interest of time, but do stop us in case you have questions. So we have created a rectangle, right? we are creating a transformation with this rectangle where we have this rectangle and we rotate it by 18 degrees 10 times. So nice trick to remember here would be the multiplication of this should be 180 because we are essentially covering the whole 180 degrees in the Cartesian plane. So this can also be something like 20 and 9. That's going to give us more crowded kind of structure. We can play around with it, but let's see what this looks like. Sahiti has raised their hand.
I just wanted to ask, can we transform colors?
Transform colors in what sense?
Like, can I play with the RGB values with, say, similar transformations? Like, if I wanted to, for example, increment red by 1 in a repeat.
Not yet. We don't have transformations that allow access to the color, but you're welcome to contribute.
Yeah, we haven't thought about transforming colors that way. That's a good question. Thanks.
Yeah, we'll be happy to help with the contributions.
Yeah. Okay, so let's see what this transformation looks like. So it's the same rectangle 10 times, right? We're repeating it 10 times. And every time it gets rotated by 18 degrees. So you see a full complete sort of figure that has come out of this. Okay, before we do the complete figure, why don't we just play with this, see what happens. So like I said, this can be 20 and 9. So this is going to give us a more crowded kind of structure, right? Okay, let's get back to the original figure. Yeah. So now we are going to make another color that's something like a tomato red. What does this color look like? I need to. This is the tomato red we have made. And we are going to make the next layer in this color. So the outer layer was the pink color. This is the next. Right. And we are going to similarly create a transformation with this. So as you can see, this gives us a similar structure. All right. Now the third layer is going to be with blue. So blue is a built-in color in Joy, so we don't have to create a blue color. What is wrong with this? Oh, sorry. We have created a blue color. And we are using that blue color. Okay. So now we'll see what the combination of this looks like. So we have created this Rangoli-like shape with only rectangles. As you saw in the process, this doesn't use anything else. So this is like a 3-layered rectangles that are rotated to create this shape. This gives a sort of an optical illusion where it looks like you have this curvatures, but this is all purely made out of rectangles. So let's give maybe a few minutes for folks to play around with colors and rotating rectangles. I hope you all have access to the GitHub gist that Kaustubh had shared in the chat. Feel free to take a look at that also.
So this spiral staircase is what, you mean okay, we didn't cover the staircase also, right?
No.
All right, okay. The spiral staircase is what we saw earlier in one of after the Sierpinski triangle. And this is the composition that's used here, the pattern that's used here, can let you create a lot of very interesting art. So let's try to play around with this. What it's doing is it's creating a rectangle first, then repeating 72 times, first rotating by 5 degrees, and then making it a little bit smaller, right? Like 92% its original size, right? That's how we can interpret this. And I'll copy this for now. Okay. So here we end up with a spiral. Right? We started with a rectangle. In each step, we made it like rotate a little bit and a little bit smaller. Right? Now we can try to repeat this pattern with a few other shapes. Right? Like the same transformation will work on any other shape. To make that idea clearer, let me call this transformation something. So let's call it a spiral transformation. I'll say TR for short. Okay. So this is a single transformation we can apply on any shape. So we'll try the same thing with some other shape. So let's start with a circle that has a radius of 50 and that is moved to the right by like 100 units, right? Let's start with the circle of radius 100 because it will get smaller later. So 100 units, that's translated to the right by, let's say 200, right? And we'll apply the same spiral transformation on this and see what we end up with. So see the spiral transformation, right? So we're taking a shape, piping it to a transformation. And when we do a show on this, we get a pattern that's something like this. Right? So you get a circle that's getting smaller and converges to the center. It, what we can also do is maybe change the parameters of the spiral transformation. Play with this a little bit. It would probably be interesting to rotate it more and scale it a little less, right? Or the scaling factor can stay the same. It will rotate it, let's say 20 times. And I'll make the circle slightly come to the left. Yeah, let's see, spiral equals C piped into the spiral transformation. Mm, okay. Yeah. So we end up with a slightly different pattern that has these interesting overlaps. One example we have here along something similar is this set of parameters for the same transformation, right? So, so this we have 36 times 4. I'm scaling by okay. So our circle is 100 units to the right. So this is a circle with radius 50 and move to the right. So what we can do now is let's say spiral equals C piped into the same spiral transformation. And what happened? Okay, I should do C spiral. Right. Okay. Yeah. So now you get like a perfectly non-overlapping group of circles that still converges to the center. And the interesting thing is you can apply the same transformation on this whole shape and you'll end up with something, right? And yeah, you're encouraged to play around with this. The code is in the document.
So Sahiti has shared a cool
Oh.
Snippet in the chat.
I'm not able to find the Zoom menu. Yeah, okay. Ah, so this is a rectangle that's getting smaller and rotating. Very cool. Yeah. Very cool. Saiti, are you referring to the error or? So how do we want to proceed? I had an interesting tessellation.
Yeah, that will be interesting to look at.
Yeah, I don't want to go too much into the implementation for now, but I think what will be more interesting for everyone is like just starting with this starter link. Like just don't look at the function. I'll explain what it does. But this is the link that you can start with. So what it does is it gives you a function called tessellate. It's a weird spelling, 2 S's and 2 L's. And it takes 2 arguments, right, this function. The tile function, so it takes one of the arguments is how many, like what is the size of each tile, right? When you set this, I want you to think that our canvas has the size 500 by 500. So if it's perfectly divisible by 500, that's better. But what tessellation is that you break down the canvas into a number of tiles and you have like a similar function running on each tile, but that's like either adapted to the to that specific tile or it's like something random, right? So this is one example where we have 25 tiles in each row, right? Each row and column, you can imagine a grid. There are 25 tiles like this, each of length 20. And so, for example, this diagonal, this thing here, this square is one tile. And each tile, for each tile, the same function is run, but the function uses like a random value. So the function I've used here is, so we have a pattern matching in OCaml. So you have this function random2. Random2 will give you either 0 or 1. So it will give you two random possibilities. Right? So it can be 0 or 1. OCaml complains when the pattern match is not exhaustive. So I had to do this catch all, right? And then we give either a diagonal that's like this or a diagonal that's like this, and you end up with a pattern that looks like a maze, right? So you can play around with this. One other cool idea for a tile function is you come up with a random radius for a circle, right? So for example, I'll again use and each tile. So for each tile for this function, you want to paint the whole canvas, right? Like for the tiling function, consider like uh, you want the tiling function to cover all the 500 by 500 canvas, and then it will be shrunk when it gets tiled. Right? So let me clear the canvas first, and I'll say let tiling function xy equals a circle with a radius of random, and we can have up to 250, right? So it's a 500 by 500 canvas. You can have a maximum radius of 250 units. X and Y doesn't matter. And when I do tessellate 20 tile function, so now we get this pattern where like you have lots of randomly sized circles. And you can do the same with like you can randomly have squares or like concentric circles or donuts. You can even have tessellations within tessellations and whatnot. So it's something to explore. One thing I glossed over here is we created a function. Yeah, it's a when you have let x equal something, that's you're creating a simple assignment. When you're doing that with more things before on the left side of the equals, you're creating a function with those parameters, right? So I can use x and y inside this function here, and yeah, they'll be part of the function body. If you want, you can play around with this function and see what you can come up with. If you have anything interesting to share, please raise your hand. I think we can just do exercises or play around now.
Hello. Yes. I was just playing around with the fact that you can nest the repeats. So I created a G which just repeated like a particular transformation, and then I took that and then rotated it like 4 to 8 times. Yeah.
It's still loading on my browser.
Oh.
Would you be able to share the screen, Sahiti, also?
Sure, I can try. Yeah. So that's hopefully that's visible.
Yeah, it was visible for
Very
me,
cool.
but I guess I hit the dropped.
Okay, I think we have time to see one more example. So I was just trying to load the Sierpinski triangle example on my browser. Okay, let me share my screen. Can you all hear me?
Yeah,
okay.
yes, we can hear you.
Okay. No, Julian had asked muted on the chat. Okay. So I've loaded the function already on my top level. So let's use this to try to figure out how this function was written, right? So basically, this is what Sierpinski triangle looks like. So you have the highest level triangle, and you have the structure inside where you have three smaller triangles, right? This gives you a very nice illusion of having smaller and smaller triangles inside. So that was level 4. Let's go step by step. So this is the level 1. And this is the level 0. Yeah, I mean, it's already displayed. Yeah, this is the level 0, where we have just the triangle, right? This is the level 1. I'm going to store the points here so that we don't have to put it again and again. Yeah. This is level 1. This is level 2. This is level 3. This is level 4. Level 5 onwards is going to be compute intensive. So it might take a while to print it. Yeah, this is a bit compute intensive. Okay, so let me try to walk through how we came up with this function, right? So what do we know? We know the biggest triangle, right? The first level of the triangle. So this is essentially 3 points that are joined to form a triangle. I have taken very simple points. So this is 0, 100. This is 100 minus 100, and this is minus 100 minus 100. This can be anything, but just for the sake of simplicity, these are the points. What happens when we try to draw the first level? So as you can see, we are having 3 smaller triangles, right? So you start from the midpoint of this, connect with the midpoint of the next side, and connect with the vertex itself. So this is being repeated for all the sides. So that's essentially what we are doing here. So if you look at the second level, take the smaller triangle and repeat the process. So you're again drawing 3 smaller triangles inside, right? So that is essentially how we came up with this function. I'll leave this as an exercise for folks to figure out. But I think it's also in the examples that we have shared in case you want to look up the solution. This was sort of really easy to encode in Joy because we have all the basics that we need to draw this. So it was it was really simple than doing it, say, in a graphics library. So Joy in the backend uses graphics libraries. We have 2 backends. There can be more backends. we have the basic OCaml graphics backend. So OCaml graphics is the default graphics library that was in the compiler, but it's no longer in the compiler. It's maintained as a separate library. We also have a Cairo backend. So there are OCaml bindings for the Cairo library, and we use that as the backend. I mean, Cairo backend is running here, I believe. Or is it SVG? SVG, okay. SVG backend is running on the browser. But if you use Joy on your machine, by default, the Cairo backend runs on your machine locally. It's easier to use the SVG backend on the browser. So this Kaustubh site setup uses the SVG backend. But yes, so there can be more backends. That doesn't matter. The aim of Joy is to give us a really simple interface that facilitates learning, essentially. So we'll leave this as an exercise. I think we have a few more minutes. So in case you all have any questions about Joy or about OCaml in general, we'll be happy to take them.
If anyone has question, they can raise their hand and I will unmute you. Yeah.
Hey, Kaustubh and Sudha, thank you. This session was more to understand the Joy library and in the process learn parts of OCaml.
Yes, indeed.
Okay. The Joy library is really cool. So thank you. It's wonderful. But what would have helped is if this was if folks had given a heads up on what was the expectation. While the workshop that tag did read beginner, I was not sure if this was what was the purpose of this specific session. But anyway, but yes, I did. So I am a literally OCaml newbie, 0, like. But this session was helpful to help me understand parts of the OCaml syntax and thereby gain some ground into getting into it. So thank you so much for that. Thank you. And
Okay,
and
that's
just another question, like I had mentioned in the chat, like if you could quickly walk through the how was the share implementation done, like what was the idea behind it, it would be helpful. Maybe you can take it offline, but yeah.
Yeah, I think it's better if we take it offline. But it was forked from one of the JS of OCaml projects. JS of OCaml is the compiler we used to get this browser interpreter, and uh, I think what they do is they just base64 encode the code and run it every time, like load it and run it every time. Interestingly, this whole project was compiled from OCaml to JavaScript, including the interpreter and all the libraries, and including the DOM part as well. Like the JavaScript that actually runs to interact with the DOM was also originally written in OCaml. So all of this uh, is like an OCaml file. It gets compiled. We have 5 more minutes. If nobody has any questions, what we could do is maybe go through a few parts of OCaml that are very idiomatic, but we didn't go into as much depth. Like, I think pattern matching is one. Lambda functions is one more.
I think we have some of those examples here. Okay, so Lambda functions are essentially anonymous functions, right? So you're creating a function, but the function doesn't have a name. So this is the base identity function. I hope one can see my screen. Yeah. Oh, this essentially takes one argument and returns the same argument. So it doesn't matter what the type of the argument is. And that is encoded in the function's type. So ID alpha to alpha, that is quote A to quote A, means it takes an argument of type quote A and returns another argument of the same type quote A. So these are like type variables. Because this can be any type and there isn't a restriction to the type, it is quote A, but I can show you plus, let's say this is +1. So I'm going to add 1 to whatever it is the argument of my function is, anonymous function is. So the type checker infers that the type of this is integer to integer, because we have done a +1 here. So the type inference is really powerful in most functional programming languages and also in OCaml. So yeah, a programmer doesn't have to worry about what the type of function needs to be tagged as, right? What does the ID function do? Let's say ID 10, it returns 10. Plus 1 to 10 again, returns 11. We can have another function called square. Is equal to, I'm taking an argument and returning its square. This is again going to be an integer to integer because this operator is specific for integer. So if I want to say I want to multiply float values, I can't use this. This might seem a bit counterintuitive in the beginning, but this is one of the one of the things encoded in OCaml. I can only multiply integers. If I want to multiply float, I have to use this asterisk dot operator where I can multiply floats. Right, so okay, going back to square. So square of 10 is 100. The square of 100 is 10,000. Square of 25. So when you're defining the function itself, it doesn't need an argument. It's going to take a lambda and operate on the lambda. This is really useful when we are doing complex things and we don't want to we don't want to have a lot of variables. Let me see if I can find a good example for pattern matching. Do you have anything handy, Kaustubh, that you want to share?
Sudha, we
think
have, I guess we are about to end. So,
all right, okay. So for folks who are interested to learn this further, I would recommend Cornell's CS3110 textbook that has interesting resources on all parts of OCaml. So I would recommend you to check that out.
yep. Thanks, Kaustubh and Sudha, for sharing your experience with us today.
Thanks for having us.